This is lesson 3 on multiple input gates. Let's recall the basic gates that we talked about in lessons 1 and 2. You remember this is the NOT gate, the AND gate, the output's 1 only if both inputs are 1, and the OR gate, in which the output is 0 only if both inputs are 0. Now the AND and OR gates, as well as the NAND and NOR and exclusive OR and exclusive NOR gates, can also have multiple inputs, more than 2. Let's look how it works for an AND gate. We could have, say, n inputs to the AND gate. And the behavior of an AND gate is that the output is high only if all inputs are high. Now in Verilog, we use this assignment statement saying assign z equals x1 and x2 and x3. In Verilog, we use square brackets for the array indices. Verilog also has what's called a reduction operator. You could just say assign z equals ampersand x. That's the same as this. You don't have to write them all out. And we can use this so-called gate instantiation statement, which will instantiate a multiple input AND gate in which the output z has these n inputs. Now in VHDL, we would write z, we use this signal assignment statement with the less than and equal sign, is x1 and x2 and, we have to write out the and symbol, you remember? And the curved brackets are used rather than the square brackets to indicate array elements in VHDL. Now we can produce this multiple input AND gate using 2 input AND gates. For example, a 4 input AND gate can be made using 3 AND gates as shown here, or this is a 3-level one. You can make a 2-level one where the output here would be x1 and x2, the output here would be x3 and x4, and you AND them all together. Turns out we can use a for loop to represent this. We can say z equals x1. This is actually a Verilog statement. You can say for I equals 2, I less than or equal to 4, and I equals I plus 1. You go through this loop until I becomes less than or equal to 4. Each time through the loop you increment I by 1. And you set z equal to z, which starts at x1, and xi. First time through it's x2, so it would be x1 and x2. The next time through it's x1 and x2 and x3. And the next time through x1 and x2 and x3 and x4. And if you implement such a Verilog statement, it would actually produce this 4-input AND gate. Let's look at a multiple input OR gate. The behavior of multiple input OR gate is that the output is low only if all inputs are low. If any of the inputs are 1, the output is 1. In Verilog, again, we use the assignment statement, assign z with the OR symbol. The reduction operator OR can be used to represent all this with just OR x, where x is an array. And we have the gate instantiation statement OR, producing the output z for the inputs x1 to xn. Again, in Verilog, you have to spell out the word OR and use the curved brackets for the array indices. You can also use this for loop to produce the 3-level or the 2-level OR gate, same way we did for the AND gate. How about an exclusive OR gate with multiple inputs? Turns out the output of a XOR gate with multiple inputs is high only if the number of high inputs is odd. In Verilog, we can use the assignment statement saying z is x1 using the hat operation, or just a single hat with the array used as a reduction operator, or this gate instantiation statement for XOR. In VHDL, we can have to write out the XOR operator. Let's see what happens if we use this for loop for the XOR. It actually will work and produce this 3-level 4-input XOR gate in terms of 2-input XOR gates. And you can verify that the output Z is 1 only if the number of 1 inputs is odd. If this is 0, 1, 0, 1, for example, the 0, 1 produces a 1. Exclusive OR with a 0 produces a 1, and exclusive OR with a 1 produces a 0. So 2 1s would be even and the output would be 0. And you can test it for other cases and convince yourself that that in fact is the case. How about a multiple input XNOR gate? In this case, the output will be high only if the number of high inputs is even, since it's just a not exclusive OR. Again, this is how you would write it in Verilog, using a not and the hat. The not hat can be used as a reduction operator, or you could use the XNOR as a gate instantiation statement. Again, in VHDL, use the XNOR word as the operator. Multiple input NAND gate. The output of a multiple input NAND gate is low only if all inputs are high. It's a generalization of, it's just a not and generalization of the 2-input one. This is what it would look like in Verilog. Again, the not ampersand can be used as a reduction operator. And in VHDL, you have to write out the operator name, NAND. Look what happens when you take a 2-input NAND gate and connect the 2 inputs together. From the truth table, the input is going to be either 0 or 1. If they're both 0, the output is 1. If they're both 1, the output is 0. So this is an equivalent to an inverter. That is a NOT gate. So you can make a NOT gate out of a NAND gate by just connecting the 2 inputs together. But look what happens if you take this NAND gate and replace the bubble. You see you'll end up with an AND gate. Since this is a NOT AND, and if you put another NOT, you get an AND gate. So you can make a AND gate with 2 NAND gates. And you remember that we can also make a NAND gate using the OR symbol with bubbles on the input. So if you put 2 NAND gates on the input and then a NOR, that is an OR gate, then you can make an OR gate then by, if you add 2 of these NAND gates. So with 3 NAND gates you can make an OR gate, which means you can make a NOT, an AND, and an OR from NAND gates. And I told you that you could make any circuit using just ANDs, ORs, and NOTs. This means you can make any circuit using just NAND gates. We call a NAND gate, therefore, a universal element. That is, it's a universal gate that can be used to make any logic circuit. Here is a multiple input NOR gate. The behavior of this is that the output of a NOR gate is high only if all inputs are low. This is the Verilog statements for making a multiple input NOR gate. And again, the VHDL, you'd have to write out the word NOR to make this multiple input NOR gate. It turns out that a NOR gate is also a universal element. We can see that by connecting the 2 inputs together also gives you an inverter. If they're both 0, the output's 1. If they're both 1, the output's 0. If we place this bubble with this NOR gate, we can make an OR gate out of 2 NOR gates. And you remember, we could make a NAND gate with 2 bubbles on the input to represent a NOR gate. and therefore we could add to those two input inverters to turn it back into an AND gate. So we can make an AND gate, an OR gate, and a NOT gate out of just NOR gates. Therefore we can make any circuit using just NOR gates. So a NOR gate is also a universal element.